and some very dear friends from Brazil. I'm pleased to have the opportunity to be able to make this presentation, and I thank Energy Simulation for making that possible. So I hold the Energy Simulation chair in CCUS reactor flow simulation, and I want to talk to you a little bit about some of the techniques that we're looking at for trying to encourage the use of GeoEnergy to help us towards the energy transition, and exploring some potential synergies that may exist between different types of process to facilitate that. So a fundamental problem we're facing, as we're all aware, is the increase in the CO2 emissions that are taking place over the course of my career. Concentrations in the atmosphere have increased by perhaps something of the order of 70, perhaps slightly more than 70 ppm. That's not uncorrelated with the fact that hydrocarbon consumption has increased over that period, and just recently we passed the 100 million barrel mark, 100 million barrel per day mark. So there's clearly a problem. CCS, as we know, is a potential mechanism for addressing that, amongst many others, of course. But the big challenge with CCS is that the technology to deliver it is expensive. And so we need to think about an approach using the subsurface that can help us address these issues. And I would say it breaks down into three aspects. The first is making oil and gas production more sustainable. We don't know how much remaining oil and gas production there will be, but it's not about to stop overnight. And so we need to make sure that we can reduce the emissions as much as possible with whatever there remains to be produced. The second thing that we should be looking at is using other sources of greener energy, and the subsurface has a role to play in that, both in terms of sources and also in terms of the energy vectors. And then we need to think about using our expertise and the facilities that we have in order to facilitate CO2 storage and try and make it a more efficient process and a more cost-effective process. And it's that I want to concentrate on primarily during this presentation. I'll touch on all three aspects. I want to present to you a team that I'm very privileged to be able to work alongside at Heriot-Watt University, comprising PhD students. I want to make a special mention to Ali, who has just defended his thesis just last week. And then the ones highlighted with the red boxes here are present with you in Rio. And in fact, I'd encourage you to go and see posters from Ahmed, from we've got Celia here, we've got Patricia, we've got Mojde, Shabnam, and Ahmed. And so go and speak to them by all means, and please have a look at their posters. I'm actually going to mention some of those posters during my presentation. I've also got an excellent colleagues that I work with, and you know Arne and Gang are with you there in Rio. And I'm sure they'll be able to take note of any questions that you may have and bring them back to me. So the first item we're going to look at is how do we make remaining oil and gas production more efficient. And the area that we're looking at is to do with managing oil field scale, particularly in the context here of carbonate reservoirs. So Mojde is looking at how to make scale inhibitor treatments more efficient. In fact, just how to understand how some particular inhibitors, referred to as phosphonate scale inhibitors, how they interact with the rock in the carbonate system, and looking at that as a function of, say, temperature and water composition and the rock mineralogy, and trying to see what we can do to extend squeeze lifetimes in such systems. So her experimental work is very useful in informing the squeeze models that we have, which we use to design treatments in the production wells. And then Patricia, who is funded by Petrobras, is working on looking at CO2 geochemical reactions that take place deep within the reservoir, and the impact that these reactions will have on the brine chemistry as it approaches the production wells, because that's obviously what's going to impact the severity of the scaling problem and when it occurs, and indeed where along the well it occurs. And her work has identified that the presence of CO2 in the reservoir be it in the oil that's originally in place, or be it injected CO2 as part of a CO2 WAG scheme, that CO2, as I say, depending on its origin, will partition into the aqueous phase, it's soluble in the aqueous phase, and will impact the reactivity. And in fact, many interactions are coupled together so that the CO2 content actually has an impact on the sulfate scaling tendency, even though the sulfate scales tend to be pH independent scales. So those are really important findings which will be taken forward into the field developments. And then the second main area is looking at how we can use what we've learnt from our understanding of oil and gas systems and apply them to other areas where we're using the subsurface for trying to deliver lower carbon energy, shall we say. So the first of these is Shabnam, who's working on scale inhibitor application in geothermal wells. Some of the same principles apply, but in fact in geothermal systems, while the drilling of the well might be the most expensive part of the process, in fact managing scale can be very significant, and sometimes scale deposition will actually stop these from functioning, and they have to be abandoned altogether. So there is some significance to this, and particularly the silicate scales are some of the hardest to prevent and to remove, certainly to remove once they've formed. So Shabnam's work has been looking at different types of scale inhibitors. These are polymeric scale inhibitors, and how they persist within the system and how their performance changes over time and what kind of concentrations are required for particular brines. Increasing temperatures gradually, so she's been working up as far as 95 degrees. We've not got very high temperatures yet, but just taking it a step at a time. And then Ahmed Reza has been working on hydrogen storage, and in particular looking at coupling bio and geochemical reactions in the porous medium, studying these in the first instance in zero-dimensional, sometimes one-dimensional models that he's built himself using MRST, and then taking these and coupling these with geochemical models, and then taking those forward to look at the impact that flow has, because we know that while we may have very good observations from laboratories on what types of reactions are taking place and what their products may be, in fact a key factor will be the availability of, say, nutrients for sulfate reducing bacteria to perform their function. And so the flow in the porous medium is also going to be an important aspect to how these reactions evolve over time. And then the third area I want to cover is on how we can manage carbon capture and storage and try and make it more financially viable. So people will criticize CCS for a variety of reasons. One thing they will state is that it's an untested technology. That's simply not true. There's over 5 decades worth of CO2 enhanced oil recovery projects in the United States involving some 140 projects in which CO2 has been injected very, very effectively. Now the primary purpose there was not initially storage, and the source of the CO2 is from natural reservoirs. But the point here is that CO2 injection at large scale is very much technically feasible. It's within our grasp to do it. The major problem is actually to do with financing it. And so the question there has been that CO2 injection has been performed for enhanced oil recovery. Can we look at taking a system and trying to take advantage of the potential for oil recovery and enhanced oil recovery to finance a greater degree of CO2 storage, and actually to set an objective of CO2 storage. So here we've got some calculations. These were actually performed by Idra Rodriguez, who's a former student of ours from Brazil, and she was looking at scaling tendency and during CO2 EOR, but also looking at how can you maximize CO2 storage in an enhanced oil recovery environment. So looking at, for example, here on the x-axis, the total amount of CO2 stored, and on the y-axis, an indication of oil recovery or net present value of the system, and comparing them with a conventional water flood, say, or even a gas flood. And so being able to identify that incremental value can be achieved from the additional hydrocarbon production, but also that there's a possibility of increasing the amount of CO2 that's actually stored during the process. And you come up with a Pareto front like this one here, and you can start to make choices about the relative impact of strategies that will increase storage without reducing incremental oil too much. And we know that in various parts of the world, CO2 is already being stored on an economic basis. So there's over 25 megatons of CO2 have been stored in aquifers in Norway, enabling hydrocarbon production in the Sleipner field and the Snøhvit field. So Norwegian regulations stipulate that taxes would have to be paid for the CO2 that would be otherwise vented, and the cost of the injection projects is lower than the taxes that would have to be paid. So in fact, for Equinor, doing CCS in these two projects makes economic sense. And then closer to home, for you folks in Brazil, Petrobras identified that by the end of 2023, 53.8 megatons of CO2 had been stored in the pre-salt carbonate oil fields. And the key thing there is that the driver for that was legislation stipulating that the CO2 that was produced with the oil from these pre-salt fields could not be vented to atmosphere. And so they had to do something with it. So here, that amount of CO2 has been stored as part of a drive towards reducing CO2 emissions to the atmosphere. Now, of course, associated with that is incremental oil production, and the incremental oil will have its own CO2 scope 3 emissions, but nonetheless, this is demonstrating that where the fiscal regime is appropriate, it is possible to have CO2 storage at scale. Indeed, Petrobras target having stored a cumulative 80 megatons by the end of this year. So this leads us to a straightforward statement that industrial scale CO2 storage is taking place today. It's driven by regulation and it adds economic value to operators, so it can be done. And the challenge for us is to see this done more extensively. So what can we do to couple oil and gas production to affordably drive down total emissions using CCS? So I want to cover one or two areas that we are looking at fairly briefly, and we'll point you to some posters and you can go and chat to the PhDs, students involved, and have a clearer and more in-depth conversation than perhaps we can manage during this 20-minute period. But the areas I want to talk about are the potential for twinning perhaps conflicting objectives, as Hydra did in her work, in order to maximize NPV and to maximize CO2 left behind. So here we've got an example of a field in the North Sea that was put under water flood, and the question that we addressed was if instead of after a certain period of time, if one were, say, 15 years of production, one were to start, one had available CO2 for performing an EOR project, what impact would that have? And what we found was we could reduce the, so the black line here represents the oil recovery that might be achieved during a 40-year water flood. And what we found was that we could cut the project duration to 35 years, and by injecting CO2 in one particular strategy, we could actually get a 5% uplift in the oil recovery, and in the same process store 53 megatons of CO2 in this fairly large reservoir. Other areas that we can perhaps look at would be using CO2 to recover oil from residual oil zones, where the oil is immobile to normal water flooding processes, but where there might be potential for both recovering that oil and, because of the nature of the system, actually leaving quite a lot of the CO2 behind. Or looking at CO2 coupled with oil and gas production to manage pressure in both, either in one structure sequentially, so doing the hydrocarbon extraction first, and then using that same structure for CO2 storage, or perhaps simultaneously where there's pressure communication between the oil field and the CO2 store. And then finally, I want to touch on temporary storage of CO2, where CO2 is currently being emitted, but there's a potential that it could be used at some point in the future, for example, for EOR. So first off, I'm going to give some reference to Ahmed's work, and he has a poster on modeling CO2 EOR in residual oil zones. So these are systems that can be quite large in some cases, which contain hydrocarbons that are otherwise unrecoverable. And so an immediate challenge is being able to initialize these models, because we don't really want to be reproducing the entire history of charging of the system, and then perhaps we don't need to model the charging of the system, but then the driving of the system through natural processes down to residual oil saturation. This may have taken place over many millennia, and we don't want to be modeling these every time. So we have to find a way of initializing these systems, but honoring the history, because the recovery process, the displacement by CO2, we know is sensitive to the history. And so Ahmed has been working assiduously on trying to identify proper ways. Now, some of the simulators do already have some techniques, but in fact they're not really, so he has actually run some models over very long periods of time to test the actual initialization of these systems, and how the systems got to the way they are just now over many millennia. And actually some of these initialization systems that exist in the simulators could do with some improvement, and he's got some recommendations to make on that. And then once we've got confidence in our ability to accurately initialize these systems, the question will be to look at opportunities for creating oil recovery, for maximizing the oil recovery, and at the same time maximize the amount of CO2 that's left behind in the system. And then Revelation here, who isn't in Brazil, but I hope she'll be able to attend future summits, has been looking at systems in South Africa where there is potential for using depleted hydrocarbon fields for subsequent CO2 storage. We know that hydrocarbon production, whether it's oil production, we maybe leave the system at its initial pressure if we do water flooding and voidage replacement, but with gas fields they will be depleted. And so the question there arises, can we use that pressure sink, if you like, that pressure hole that's been created by natural gas production in order to increase our storage capacity and security. Got an example here of a system. This is actually not in South Africa, it's in the North Sea, where we have plot pressure as a function of distance along a certain path. It's about a 100-kilometer long path in the system. Actually published work from the Captain Fairway in the North Sea, and the Captain Fairway is a gently dipping structure. So as we go from west to east, it's getting deeper, and so what we're plotting here is the initial hydrostatic pressure in the system, with the GoldenEye field is located here. And GoldenEye went through 9 years of production, which reduced the pressure by something of the order of 100 bars as the gas and the gas condensate was produced. And we looked at what would happen if, say, 5 years after cessation of production, we were to start using the system as a store. But one thing to bear in mind is that we're no longer at static equilibrium after the end of production, and so a process called aquifer recharge would take place over that 5-year interlude. And as a consequence of that, we might lose 30 or 40 bars of pressure as aquifer water is flowing back into the space. But it would still allow for CO2 injection, so we modeled 5 years of CO2 injection And we found that we're able to inject something of the order, if memory serves, about 90 megatons of CO2 into that system without breaching the original hydrostatic pressure limit. So that's showing a typical example of being able to use a past hydrocarbon field for future CO2 storage, but also the importance of time. Other factors that we need to take into consideration when we're comparing aquifer storage with storing in depleted hydrocarbon systems is that the whatever stranded hydrocarbons are remaining in the system, they will tend to increase the compressibility of the system. Obviously, water's got a very low compressibility, lower than that of rock. Actually, CO2 tends to be much more soluble in oil than it is in water, so there's additional solubility trapping. Here's a calculation. This is from a previous work done on a South African system, where in storing CO2 in this particular oil reservoir, perhaps 5% of the injected CO2 would dissolve in the aqueous phase, but it would be possible to get over a 100-year period over a third of the CO2 dissolved in the oil phase, which was trapped. And then there are impacts on mobility. We've got three-phase flow. You might imagine that would reduce the mobility. Actually, because natural gas methane, for example, is less dense and less viscous and less soluble in water than CO2, those three factors will actually mean that a plume of a mixture of CO2 and methane will travel faster and further than a plume of pure CO2 would. And so we do need to be cautious with the concept of injecting into depleted systems and what the impact that will have, not only on the pressure footprint, but also on the migration of the CO2 plume. And then we might also think about using CO2 for injection into adjacent structures simultaneously. So not so much looking at CO2 EOR, where the CO2 is actually injected into the oil field, but perhaps if there's an adjacent trap with a connecting pore volume that is communicating, and not looking to have the CO2 molecules themselves entering the oil field, but looking to have the pressure response, the two of them supporting each other in some way. So as we pressure up the CO2 store, that pressure will transmit through the aquifer and could be used to replace or perhaps partially replace water injection that's taking place in an oil reservoir. At the same time, the reduction in pressure due to the oil production could be a benefit for the CO2 store and actually allow increased storage capacity. So it's just a case of looking for these opportunities where adjacency of a CO2 store to a currently being operated oil field could be managed in such a way that we don't have to worry about whether the CO2 will enter the oil field, but where there may be some mutual synergistic benefit from the pressure in terms of pressure management between the two of them. And then the final thing I want to put before you is a fairly new concept, certainly a new concept to me, which is temporary CO2 storage. Now, why on earth would you want to do that? Well, this is Farah. She's funded by a Kuwait oil company, and she's looking at a particular field example where currently there's something of the order of 1.5 to 2 megatons of CO2 being separated and vented to atmosphere at the moment. They're thinking about the potential for doing a CO2 EOR project relatively nearby at some point in the future. And so the question there is, the CO2 that's currently being vented to atmosphere, would it be possible to capture that, store that temporarily, and then produce it again in support of the EOR project when it starts up? Obviously, when the EOR project starts up, the CO2 that's currently being vented to atmosphere would, at that time it's being vented to atmosphere, would then be directed straight to the EOR project. But the question here then is, can we avoid emitting CO2 to the atmosphere in the interim before that CO2 EOR project starts up? And can we actually use that CO2 to benefit the EOR project? And so what would the question for her is, what would the design of such a project look like compared to the design of permanent storage project. And so far she's identifying that perhaps you could end up, if you work at it, storing somewhat over 50% of the stored CO2, perhaps something over 50% of that stored CO2 could in fact be recovered again within a reasonable time frame for use in the EOR project. But then that means that there's another 50% that's being left behind. Would we classify that as a waste? Well, it's a waste, but it's better being left behind in the subsurface than it is in the atmosphere. And furthermore, having used the financial driver of the EOR project to construct this temporary storage system, if her work demonstrates that the economics work out, and we don't know that yet, but if it does, then that means that there will be infrastructure in place that even once the EOR project has stopped, once the last barrel of oil has been produced from the system, there'll still be the potential for using the system that was initially used as a temporary store, now using it as a permanent store and continuing to inject CO2 into it. So in conclusion, in our work, we are looking at three things. We're looking at how to make current oil recovery processes more efficient and more cost effective, but also to reduce the emissions associated with them. Secondly, we want to apply what we can learn from oil and gas activity to other aspects of geoenergy management, such as, for example, hydrogen generation and storage, and also geothermal production. And then finally, we want to see how we can interweave CO2 storage and remaining hydrocarbon production, primarily as a means of financing, so using hydrocarbon production to finance the CO2 storage. And so that means looking for synergistic opportunities, such as managing pressure either in time or at the same time in various parts of the connected pore system in space. And looking at finally looking at storing current day CO2 emissions, accelerating that storage process with a view to temporary usage for future EOR projects, then carrying that infrastructure forward for permanent storage. So with that, I want to acknowledge Energy Simulation for their kind support for this work. I want to acknowledge the companies that supplied software that we use, CMG and SLB in particular, and the partners at various universities and the funders of this work. And I'd like to thank you for your attention.